So in order to do this, we need to learn how to represent each of these baskets. Here is the list of baskets as presented a few slides ago. Instead of representing it this way, we think of it as an indicator of an item being present in a particular person's basket. For example, if we look at the first person, then we would have a 1 for bread, a 1 for milk, and a 0 for the other objects. If we assume that there are only these 4 objects that can be purchased, this person purchases bread and milk, and so there's a 1 under those 2 items and a 0 under everything else. And that corresponds to the set bread and milk. Similarly, if we look at the 5th person, this person bought bread, milk, diapers, and cola, but did not buy beer and eggs, and so there's a 1 for the items that appear in that person's basket and a 0 for the items that don't appear in that person's basket. So this is how we think of representing the data that we want to now process. So our goal now is to find the subsets of these 6 items in this toy example that tend to co-occur together with high probability, meaning in this case the high probability is simply saying a probability above some threshold that we're going to set. So for example, we might ask, do the objects bread and milk occur together relatively frequently in a person's basket? So what do? We simply go to each of the 5 baskets and we count the number of times that bread and milk co-occurred in both. So we have 1 time here, a 2nd time, and a 3rd time. So 3 out of the 5 baskets contain both bread and milk. That's 60%. And so therefore we would say, okay, these 2 objects co-occur with high probability from this very simple data set. So notice that in this case, a person's basket can contain more objects than just those 2. For example, the 5th person also has diapers and cola, but we're only checking for the subset bread and milk, and so we disregard everything else. So it seems like a straightforward and trivial problem, and when the data is small, it is. We simply have to brute force count every subset. However, in real life, the data sets that we're looking for don't have 5 different objects and 6 items. We might have 100 million users or customers, and there might be on the order of thousands of objects that they could purchase or view. So there's a very large number of users and objects making up this chart. So we can do some quick combinatorics to figure out why brute force search is not going to be possible in this case. For example, we can ask how many different subsets of items are there that we could possibly check. So this is saying how many of these subsets k of the integers 1 to p are there that we have to check as a potentially interesting subset of objects. To answer this, we can represent each subset k as a binary vector of length p, where a 1 indicates that the object is in that subset and a 0 indicates that an object is not in that subset. And so the total number of these binary vectors, meaning the total number of potential subsets k that we would have to check, is 2 to the p. So this is a very large number as soon as p gets even moderately big. So it's not possible to check every single possible subset by brute force counting. Okay, so then we might say that, well, clearly nobody will have a basket with every item in it, and if p is very large, we could upper bound the number of items that we want to check to k. So we only care about checking subsets of k objects picked from p, a superset of p total objects. So in this case, we can still do the combinatorial analysis to ask how many different subsets of size k can we construct from a superset of size p. And the answer to this is p choose k, which is p factorial divided by k factorial times p minus k factorial. So this is also a huge number. For example, if p is 10,000, so if there are 10,000 total objects, and k is only 5, meaning that, for example, if a store has 10,000 total objects for sale, but we're only going to check subsets of 5 objects as being of potential interest, then p choose k is still 10 to the 18. So that's 10 to the 18 different subsets that we would have to check by a brute force search, which again is too large to do in a reasonable amount of time. So the takeaway is that intuitively, what we're trying to do is extremely simple. We have n of these different baskets. For example, we could have several millions of rows in this table, and each row is going to say that this customer purchased a certain subset of items. And all we're looking to do is find subsets that tend to occur a lot, that tend to be purchased together very frequently. The problem is that we can't do a brute force search over all of the subsets to actually count the number of times that these subsets occur with each other. And so we need some sort of an algorithm in order to help us do an efficient counting. And so we can't do a brute force search, so we need some sort of a clever approach to handling this counting problem. So before we discuss the algorithm for finding all of the subsets of potential interest, we first need to ask, what is it that we want to count? So again, let's let k be a subset of p objects. So k is a subset of the p integers. And we're going to let a and b be 2 subsets of k, such that the union of those 2 subsets is k, and a intersected with b is the null set. So in other words, we let k be a subset of the superset 1 to p, and then we define a and b to be a partition of k into 2 disjoint sets. There are 3 probabilities that we're interested in computing. The first is simply the probability of the set k, which can also be written as the joint probability of a and p. This is called the prevalence or the support of the items in set k. So we want to find all subsets k such that that combination in that subset co-occurs very often. So it co-occurs with a high frequency in the data that we have. Another thing we would want to compute is the conditional probability of the set B given the set A. So if you tell me that the set A is in my basket, what is the probability that the items in the set B are also in my basket? So this is the conditional probability. This can be written as the joint probability of A and B divided by the marginal probability of A. And since A and B is simply k, that's the probability of k divided by the probability of A. So this is called the confidence. This is the confidence that B will appear in the basket given that A is in the basket. We use this confidence to define rules. So we want to find high probability sets A and B such that if you tell me A is in the basket, then with high probability B is also in the basket. We want to learn from the data what are these sets. We want to construct all of these potential sets of interest with high probability. Finally, we define this function L of A and B. This is the joint probability of A and B divided by the marginal probability of A times the marginal probability of B. So we can simplify this first fraction A and B divided by A by recognizing that this fraction is simply this marginal distribution. So in other words, we want the conditional probability of B given A divided by the marginal probability of B. So this is called the lift of the rule A implies B. This is a measure of how much more confident we are in B given that we see A. So the set B has a certain prevalence in the data set by itself. And now we want to know how much more confident are we in the set B being contained in the basket given that you tell me A is in the basket, compared to simply the prevalence of B overall. So let's look at an example, a simple intuitive example where we define K to be the set of 3 objects, peanut butter, jelly, and bread. So K has 3 items in it, peanut butter, jelly, and bread. Then we partition this so that A is peanut butter and jelly, and B is bread. So A and B do not share any items, and the union of A and B is equal to K. So this is the partition of K, A, and B. So if you tell me that a prevalence of 0.03, that the set K has a prevalence of 0.03, that means that if I look at all of the data that I have, all of the purchases that I have, the 3 items, peanut butter, jelly, and bread, appeared together in 3% of those purchases. If you tell me that the confidence of B given A is 0.82, what that means is that when peanut butter and jelly were purchased, then 82% of the time bread was also purchased. So if I simply restrict myself to looking at the baskets that have peanut butter and jelly in them, and then I throw away every other basket in my data set, then in 82% of those baskets that I'm restricting myself to, bread will also be contained in that basket. And then finally, if you tell me that the set that B and A have a lift of 1.95, so if you tell me that that L, A, and B equals 1.95, then what that means is that it's 1.95 times more probable that bread will be purchased given that peanut butter and jelly were purchased compared to the probability of bread being purchased at all. So again, this is P of B given A divided by P of B. And so what I am going to do is I'm going to look at all n data points that I have. I'm going to count how many times bread was purchased in those n objects. So the fraction of the n baskets that have bread purchased, that's P of B. And then the fraction of the baskets that have bread purchased restricted to the baskets that already have peanut butter and jelly purchased, that's P of B given A. This fraction says what's the lift or the bump in probability that I get. If you tell me A, how much more confident am I in B compared to to how confident I was in B without any knowledge. So with those 3 probabilities of interest in mind, that leads us to the a priori algorithm. So this is the name of the algorithm that allows us to very quickly find all of the subsets K that have empirical probability greater than a predefined threshold T. So remember, there are 2 to the P different subsets that I can construct in K. And I want to find all of those subsets that have an empirical probability greater than T, which I'm going to set that number T. The a priori algorithm is going to give me a way to find every single one of those subsets without actually having to search all 2 to the P subsets. So if I find a subset K that satisfies this probability, what that means is that the items in subset K will appear in at least n times T of the n baskets that I have. And we believe that a very small fraction of subsets should satisfy that, so we're going to set T such that that's the case. So what the a priori algorithm is going to do is it's going to restrict the number of subsets that we actually need to check by using simple rules of logic. So it's going to start by constructing all subsets of size 1. So it's going to first check every single subset of size 1. It's then going to have some subsets surviving, some not surviving, and then based on that it's going to move on to subsets of size 2, and so on. And only the subsets when we're at subsets of size k, only the subsets of size k minus 1 that survive this process are going to factor in when constructing subsets of size k to check. And so what's important about the algorithm we're going to discuss is that it's going to find every single subset such that the empirical probability of that subset is greater than t. But it's going to, again, use certain properties about probabilities to eliminate subsets without even bothering to check them. So this structure can be put into a lattice representation, and we'll return to this figure later. So we start with subsets, the null subset, so this is the subset with nothing in it. And then we can move on to subsets of size 1. So if we have 5 objects, if p is equal to 5, then we label them A, B, C, D, and E. Then we have all of the 5 subsets of size 1 to check. And then we move on to all subsets of size 2. And so here we have all subsets of size 2. We can then move on to all subsets of size 3, all subsets of size 4, and finally all subsets of size 5. And because there are only 5 different objects in this example, there's only one subset there. And so we can represent all of the subsets that we want to check as this lattice structure.